Our journey begins not with a software code or a flickering screen, but with a physical ritual of disassembly. To create the visual guide for this odyssey, we didn't just rely on abstract blueprints. We took real, physical components and systematically stripped them down. Every screw was turned, every thermal pad peeled back, and every integrated circuit exposed to the air. Using a process of high-resolution photogrammetry and 3D reconstruction, these physical fragments were transformed into digital twins. By photographing these parts from thousands of angles and using advanced scanning techniques, we've built a 3D model that allows us to fly through the hardware. We are moving beyond the black box mentality. We aren't just looking at a motherboard. We are exploring a three-dimensional city. This method ensures that what you see is grounded in the physical reality of copper, gold, and silicon, providing an inside-out perspective that makes the microscopic structures of a computer finally visible to the human eye. At the center of this digital metropolis sits the central processing unit, or the CPU. To the naked eye, it's a small, silver-capped square, unassuming and cold. But as we zoom in, we see the packaging, a complex sandwich of materials designed to protect the fragile heart within and provide a bridge to the outside world. Beneath the integrated heat spreader, the silver lid, lies the die. A thin sliver of silicon etched with a precision that makes the finest jewelry look like crude stone tools. This die is connected to the motherboard through thousands of tiny gold-plated contact points. When we dive deeper into the silicon itself, we encounter the true miracle of modern engineering: billions of transistors. These are the fundamental switches of the digital age. Imagine a maze so complex that its paths are measured in nanometers of scale, where the laws of classical physics start to blur into quantum mechanics. These transistors are arranged into cores, the individual brains that allow the CPU to multitask, processing billions of instructions every second. It is a dense, multi-layered grid of metal interconnects, highways of copper and tungsten that allow these cores to communicate, creating the computational throughput that powers everything from a simple calculator to a complex flight simulator. The CPU is not just a collection of cores. It is a highly organized society. Surrounding the computational cores are vital subsystems that ensure the brain doesn't starve for data. First, we encounter the shared cache, a high-speed storage area that keeps frequently used data within arm's reach of the cores, preventing them from having to wait on the slower system memory. Then, there is the interconnect ring, a high-speed data highway that circles the internal components, allowing data to zip between cores, the cache, and the integrated graphics unit. We also find the memory controller, the gatekeeper that manages the flow of information to and from the RAM, and the system agent. The system agent is the CPU's diplomat. It manages the communication pathways, like PCIe lanes that connect the processor to the rest of the computer, ensuring that the graphics card and the storage drive stay in sync with the CPU's lightning-fast pace. It is a masterclass in spatial efficiency, where every micrometer of silicon is utilized to maximize speed and minimize delay. If the CPU is the brain, the motherboard is the body's nervous system and skeletal structure combined. It is a vast printed circuit board, PCB, a landscape of green, black, or blue fiberglass threaded with miles of microscopic copper traces. These traces are the wires that carry signals between components, etched into multiple layers within the board itself. Tucked away on this board is the chipset. While the CPU handles the heavy mathematical lifting, the chipset acts as the grand conductor of the peripheral orchestra. It manages the data flowing from your USB ports, your networking chips, your SATA storage drives, and various slower PCIe slots. It's the central hub that routes lower priority traffic, freeing up the CPU to focus on the high-speed direct connections. Without the motherboard's complex routing and the chipset's organizational prowess, the computer would be nothing more than a collection of silent, disconnected parts. Computers do not run on magic. They run on precisely regulated electricity, and in that process, they get incredibly hot. This brings us to the VRM, or voltage regulator module. This cluster of components, MOSFETs, chokes, and capacitors sits near the CPU. As these billions of transistors flip on and off, they generate heat, a lot of it. To prevent the silicon from melting, we explore the cooling system. In our dissection, we look at a liquid cooling loop. A pump sits directly atop the CPU, circulating a specialized coolant. This liquid absorbs the heat and travels through tubes to a radiator. There, a series of fans blow air across thin metal fins, dissipating the heat into the room. It is a continuous cycle of thermal management, a mechanical sweat system that allows the digital components to push their limits without self-destructing. Behind every great machine is a source of energy. The power supply unit, PSU, is perhaps the most underrated component in a computer. It is the bridge between the high-voltage alternating current, AC, from your wall outlet and the delicate direct current, DC, needed by the electronics. Inside the PSU's metal box, we find a forest of large capacitors, transformers, and heavy-duty circuitry. It performs a dangerous dance, isolating the high-voltage side from the low-voltage side to ensure that a power surge doesn't fry your expensive components. It splits the electricity into various rails, 3.3 volts, 5 volts, and 12 volts to feed everything from a low-power LED to a power-hungry graphics card. The PSU is the unsung hero, the steady heart that ensures every other part of the system has the blood it needs to function. As we pause our tour for a moment, it's worth reflecting on the sheer multidisciplinary genius required to build a PC. To understand a computer, you must understand physics, chemistry, electrical engineering, material science, and logic. No single person can master every facet of this machine. It is the collective achievement of humanity. This theme of lifelong, multidisciplinary learning is what drives us forward. It's why platforms that encourage curiosity, like the ones that sponsor these deep dives, are so essential. They remind us that the world is not just a series of things, but a series of interconnected systems waiting to be understood. Now, we turn our attention to the powerhouse of the visual age, the graphics processing unit, GPU. If the CPU is a brilliant professor capable of solving any complex problem, the GPU is a massive factory filled with thousands of specialized workers. When we open the graphics card, we see a layout similar to the motherboard but optimized for one thing: speed. Beneath the massive fans and heat pipes lies the GPU die, surrounded by high-speed VRAM, video RAM. The GPU die is divided into clustered multiprocessors. Unlike the CPU, which might have 8 or 16 powerful cores, a GPU has thousands of smaller, simpler cores. These cores are designed for one specific task: math. Specifically, the kind of math required to calculate the color and position of pixels on a screen. With its massive memory interface, the GPU can move enormous amounts of data simultaneously, allowing it to render complex 3D worlds in real time. To understand why we need both a CPU and a GPU, imagine you have to paint a giant mural. The CPU is like a master artist. He is very smart and can paint incredible detail, but he only has 2 hands. He can only paint one small section at a time. This is serial processing. The GPU, on the other hand, is like 10,000 apprentices. Each apprentice isn't nearly as smart as the master artist, and they can only paint one specific color in one specific square. But because there are 10,000 of them, they can all touch the canvas at the exact same time. This is parallel processing. For tasks like video rendering, crypto mining, or AI training, the GPU's ability to do thousands of simple things at once makes it infinitely faster than even the world's best CPU. Creating this journey was no small feat. The 3D models you see are the result of hundreds of hours of painstaking labor. Sometimes, the parts we sourced didn't perfectly match perhaps a motherboard from one year and a CPU from another, but the goal was always to represent the functional reality of the machine. The production of such a visual feast requires its own kind of processing power, the human kind. It involves thousands of photos, dozens of software crashes, and a relentless pursuit of accuracy. This effort is a tribute to the viewers who support these projects, proving that there is a deep communal hunger for understanding the complexity of our world. As we move back into the system's architecture, we encounter the dynamic random access memory, DRAM. If the SSD is the computer's long-term library, DRAM is its short-term scratch pad. When you open an application, the CPU pulls that data from the slow storage and puts it into the fast DRAM. Inside a DRAM chip, we find a vast, microscopic grid of cells. Each cell consists of a single transistor and a single capacitor. The capacitor holds a small electrical charge, 1 if it's charged, a 0 if it's empty. But capacitors leak. They are like buckets with small holes. To keep the data alive, the memory controller must refresh these cells thousands of times every second, topping off the charge. This is why it's called dynamic memory. It is in a constant state of flux, incredibly fast but entirely volatile. If the power goes out, the bucket's empty and the data vanishes. For permanent storage, we look to the solid-state drive, SSD. Unlike the volatile DRAM, the SD uses NAND flash memory, which can hold onto its data even when the power is off. Inside an SSD, the engineering moves into the third dimension. We see 3D NAND, where memory cells are not just laid out on a flat plane but are stacked on top of each other like a digital skyscraper. This allows for massive storage capacities in a tiny footprint. These drives use charge-trap cells to store electrons securely. The SSD also contains its own controller and a small amount of DRAM to keep track of where all that data is stored. While it's slower than system RAM, it's orders of magnitude faster than the spinning disks of the past, allowing your computer to boot in seconds rather than minutes. In a world of silent silicon, the hard disk drive, HDD, is a beautiful mechanical anachronism. Inside, we find polished platters made of glass or aluminum, coated in a magnetic material. These platters spin at thousands of revolutions per minute. A tiny read-write head hovers just nanometers above the spinning surface, then a human hair using magnetism to flip the polarity of microscopic domains on the disk. This represents the binary 1 south and 0 south, while HDDs are much slower than SSDs because they have to wait for the physical disk to spin to the right spot. They remain the kings of cost-effective storage. For the price of a small SSD, you can get a massive HDD capable of holding terabytes of data, making them the warehouses of the digital world. Finally, we exit the box and look at the tools that connect us to the machine, the mouse and the keyboard. Inside a modern optical mouse, we find a tiny camera and an LED. The camera takes thousands of pictures of the desk surface every second. A specialized chip compares these images to see which way the mouse is moving, a feat of high-speed image processing in the palm of your hand. Inside the keyboard, we find a simple but elegant key matrix. When you press a key, you complete an electrical circuit on a flexible plastic sheet. The keyboard, as controller, detects which row and column were connected and sends the corresponding scan code to the computer. It is the humble bridge between human intent and machine action. As we reassemble our digital model and zoom back out to the familiar view of a desktop computer, we are left with a sense of awe. What we often treat as a mere tool is, in reality, the pinnacle of human ingenuity. Every part we explored, from the high-voltage transformers in the PSU to the nanoscopic transistors in the CPU, is a testament to our desire to solve problems and expand the boundaries of the possible. Engineering education isn't just about learning how to build things. It's about learning how to see the world. It's about realizing that the magic of technology is actually a series of logical, beautiful, and understandable steps. We thank the engineers who design these marvels, the sponsors who make this education possible, and you, the viewer, for having the curiosity to look inside. The journey doesn't end here. Every day, the structures get smaller, the speeds get faster, and the ghost in the machine gets a little bit more complex. Keep exploring, keep questioning, and never stop looking beneath the surface. Thank you so much for joining me on this deep dive today. Wishing you all the very best of health and happiness. And if you found this journey as fascinating as I did, please consider hitting that subscribe button and ringing the bell so you don't miss our next adventure into the heart of technology.